Hey, this is Horner, and this is the next part of the notes for the conservation of energy and work. So the law of conservation of energy, you've already kind of know what this is. The total mechanical energy is equal to the sum of all the potential energies plus the sum of all the kinetics. So remember, potential energy could be gravitational potential, it could be spring potential. Kinetic energy could be just linear, or we also call that translational. It also could be rotational kinetic energy. So here's the full law. So sometimes they'll put the final first and then the initial last. Sometimes they'll have the initial first and the final last. So it really won't matter kind of what you're doing. For the conservation of mechanical energy, this is a good problem-solving strategy. You should look for a system that's isolated and doesn't have any other friction or losses of mechanical energy. If it does, that is what we call a non-conservative system. So we'll look at non-conservative versus conservative systems later. Try to draw a picture, even if it's just stick figures, that's fine. Try to define all the symbols, list all your values, make sure you know what you're trying to find. That math representation, remember it is this, but each one of these has many different types, so you have to be careful. Check that your result does have the correct units. It's reasonable, so if you get 1,000,000 for something that shouldn't be 1,000,000, you'll know that you've done something wrong. And make sure it does answer the question. So those are some problem-solving hints that should help. If you look at pendulums, remember a pendulum, if you just put a ball on a string and you pull it back, when you pull it back, we know that it has all potential energy defined by the lowest point where it will swing through. So this distance here, or change in position, is actually your height. So when you see this mgh, that is what the height is. 1/2 mv max. Vmax is going to occur right here. So this is where Vmax is going to be. So at the highest point, it is all potential energy due to gravity. At the lowest point, it is all kinetic energy, and then it comes back to this side. Now, in a real system, the potential energy here is going to be bigger than it is here, and then the kinetic energy will decrease each time because you'll have air friction. So as long as there's no friction, no frictional effects, there's no heat being lost or anything like that, then this system should conserve energy. If we take a look at the next thing, this is all about Hooke's law and elastic energy. I will put the solutions to this on Canvas so that you can see them. Pretty nice little worksheet that we did in AP Physics 1. Goes through and really helps you define and remember all the things that go along with this. It even includes a little bit of static friction there so that you can take a look and see how that affects the system. This next part is on restoring forces and Hooke's law. So if you take a spring and you pull it out and let go, the restoring force is the force that wants to pull it back to the original shape. Same thing happens when you collapse a spring. So if you compress a spring, if I would push the spring to here, it wants to go back the other way. Because of that, we will say that the stretch is always going to be negative. No matter whether you're pulling it this way or you're moving it this way, you're going to get what we call a negative displacement. So that would be negative delta x. If I come this way, it would also be negative delta x. This happens, you'll get used to it. Hopefully that will be solved in a new version of Acrobat. So here is basically what's happening. We do have a displacement, so it's getting stretched out, and you'll see that. For a spring, if we plot the force versus that stretch, and they're going to use delta S here, so we've talked about we can use delta X. A lot of colleges and textbooks use delta S for the German. For it's supposed to be displacement, but really it's distance, which is kind of strange. So in equilibrium, the force of the spring is equal to the force of gravity, which is equal to mg. So when you have this spring and it's just sitting here, this is our new equilibrium spot. So this is our original unstretched spring. This is after we add some mass to it. And so if I measure that and put it here, I measure the force on the spring and then plot it. This gives me a Newton per meter, which is the slope of which is a K value. And the K value, remember, is just the value that tells you how stretchy the spring is. Hooke's law basically just says that the force of a spring is equal to negative. So remember that anytime we stretch or compress a spring, that change in position is going to be negative. So we'll want to remember that as we kind of go through and do some of these things. So I'm going to put that there so there's a dot. The sign is always opposite to the sign of delta S, so the sign of the force is always opposite to the sign of the stretch. So here force is positive, so we get a negative K delta S. So this is Hooke's law, and that is on your AP Physics C equation sheet. So elastic potential energy or elastics potential energy, start with a picture. So here's our picture. We compress this spring, and then when we let go, it is shot out with a velocity. So what they'd like for us to do here is we're going to start with Newton's second law for the ball, and then we're going to end up with some calculus. So we're going to go through and we're going to derive the potential energy of a spring equation. We will be using the chain rule again, so just something that we can kind of get used to as we go through. First thing we're going to say is the sum of the forces for the spring are equal to the mass times the acceleration of said spring, and that's equal to, remember, we're going to make the acceleration dv, so this is the spring, this is the velocity in that direction, over dt. And dv over dt, remember, is acceleration. Our net force here, if you remember, we said that force is equal to negative k, and then we're going to use delta S so that we just get used to that. That net force then, so this is this side, we're just going to draw an arrow down, is equal to negative k, and then here we're going to use S minus, and then we're going to call this SE. So this is when we are at equilibrium. Let's go ahead and set the two things equal to each other. So we're going to say here m dv s over dt is equal to negative k times s minus se. So that's really just the change in the position of the spring. So let's go through, we're going to use the chain rule. So remember, that's dvs over dt. We don't want dt, instead we want ds, because we want to look at the velocity in terms of the actual stretch of the system. So here we're going to say dvs, and then on the bottom, remember, we want to put ds. The only way I can put ds on the bottom is if I also put ds on the top, and then our missing variable that we had before was dt. At this point, we know that ds over dt is just like dx over dt, so that's velocity. So here's the velocity of the spring, and then we're going to take that times dvs, that's what we have here, over ds. So now we've applied the chain rule. Let's go ahead and we're going to take this and put it back in up top, and so we're putting it in for our what we had here. So instead of this dv over dt, we're going to use this expression. Our mass stays the same, so now we have m times vs times dvs over dt, and that's equal to negative k times s minus se. We're going to multiply both of these sides here by ds. So we're going to multiply, so let's just say multiply by ds. So we want to multiply both sides by ds, and when we do that, we end up with m vs dvs is equal to, oops, you know what, this on the bottom is actually ds, sorry. So we're going to multiply both sides, you're probably confused by that, multiply both sides by ds. When I do that, I get m vs dvs because the ds's will cancel. And then on this side, I'm going to get negative k times s minus se times ds. Okay, so why did we do that? Because now we need to integrate. So now we need to integrate. So let's go through and integrate. We know that on the left side, we've got m Vs dVs is equal to negative k times the quantity S minus SE ds. So here we've got Vs dVs, and here we've got S minus SE ds. And so now we can integrate because we have our two things that we want to go through and use our integration rule on. So we're going from an original speed to a final speed. And we are also going from an original position for the spring to a final position for the spring. So that allows us to integrate both sides. If we had the original equation, we can't integrate both sides. Now we can because of the chain rule and multiplying through by ds, which makes it a lot easier. If we go through and do that, let's go through and do this. Let's define u is equal to S minus SE. Okay, so we're going to say u is going to be equal to S minus SE. So instead of ds, we're going to now have du because we don't want this subtraction on the inside. We don't want to see that. And so that ds is going to become du. U becomes S minus SE. And so instead of this thing, we're going to have u du. So that will make it a lot easier. Let's go through and actually do the integration now. Let's go through and do the integration. So instead of doing this, let's do this. We know this side, when we integrate it, is going to end up being 1/2, and then we're going to have mass. And remember, your v here becomes v squared over 2, so that's where the 2 comes from. And that is your final velocity minus 1/2 of your mass times your original velocity squared. So all I did was I integrated this side. When you integrate this side, this thing goes away. And then we're going to take 1 plus 1 here. Oops, sorry, 1 plus 1 is 2 over the sum. And so here's v squared over 2. Then we subtracted our original, so we always start with 1 and then kind of move to the other. Now that we've done that, we're going to integrate the other side. So on the other side, this is going to be equal to, remember we said that we've changed it. So let's take this and move it here. We're going to have negative k, and we have the integration still from SO to SF, but we've defined this as u du. So this is going to be equal to negative, and then our u, when we go through, well, let's put our k in since that's our constant on the outside. When we integrate this, we're going to get u, and then we're going to say u to the 1 plus 1 is 2, so that's u squared over 2. And we've got to integrate this from the SO to the SF. So now our u is going to become these, and we're going to be equal to negative, and then we're going to do 1/2, and this is k times, now we're going to say u, remember, is the change. This is the change in the final spring squared, plus, and then this is going to be 1/2 of k times the original spring change squared. Okay. Now we're not done. We need to go through and just make sure we get everything in the right position. So we've gone through, we've done this. Let's go ahead and let's put everything on the correct side so that everything looks right. So this is going to be 1/2 mvf squared plus 1/2, and then this is going to be k times delta SF, delta SF squared, and that's equal to 1/2 mv original squared plus 1/2 of k, and this is delta S original squared. We know that this is the potential energy due to a spring. We know that this is kinetic energy. So in the end, we're ending up with Kf plus USF is equal to the original kinetic energy. That's original kinetic energy plus our final spring energy. So that's the derivation that you'll probably go through in college in order to see what's going on in terms of a spring. I think the only thing I really need to clean up is when we change this here, we probably need to put a delta SF and a delta SO, because remember, U is the change in those, and that should make that work out a lot better. Alrighty, that is the end of this section.